Hi, my name is Kalle Rutanen. This is O-Notation in Algorithm Analysis, Part 3, O-Notation in Practice. Recall from Part 1 that linear dominance is a relation on the coast functions defined by f is dominated by g if there exists a positive real number c such that f is at most c times g at every point. O-Notation on X is defined by OF is the set of those coast functions which are dominated by f. We can also define related notations. The first one is little o f, which is the set of those functions which are strictly dominated by f. Little omega f, which is the set of those functions which strictly dominate f. Big omega f, which is the set of those functions which dominate f. And theta f, which is the set of those functions which are equivalent to f. O-Notation is used instead of the dominance relation because it removes the need to explicitly name coast functions. For example, we showed previously that exponential search is in the set O log 2 ks plus 2. As an abbreviation, we say that exponential search coasts O log ks plus 2. Suppose algorithm A coasts OFA and algorithm B coasts OFB. Then we can define addition between the O sets and show it to be equal to OFA plus FB. This provides the cause of running algorithms A and B one after another in O-Notation. By lifting operations to O sets, we can compute the coast function in O-Notation of an algorithm by combining O sets without the need to know what the underlying coast functions are. A unary operator on non-negative real numbers is a function O minus from non-negative real numbers to non-negative real numbers. We can extend a unary operator to coast functions so that if we have a function from x to non-negative real numbers, then O minus f is a function whose value at x is given by the O minus of fx. We can further extend the operator to sets of coast functions, so that if A is a set of coast functions, then O minus A is the set of those functions which are obtained by taking the O minus of each function in A. A binary operator on non-negative real numbers is a function O plus from pairs of non-negative real numbers to non-negative real numbers. We extend the binary operator to coast functions by f O plus g is a function whose value at x is given by fx O plus gx. The binary operator is extended to sets of coast functions by if A and B are sets of coast functions, then A O plus B is the set of coast functions which are obtained by taking f from A, g from B, and taking the f O plus g. If we lift these operators to O sets, then we can prove the following cheat sheet for O-Notation. Recall that a coast function is a function from the input set to non-negative real numbers. A coast function can be too complex to get an intuition to, or even to have a closed form expression. To simplify, we need a way to group the input set and a way to summarize the coast inside each group. A grouping provides for each input the group it belongs to. And a grouping is a function from the input set to another set. For example, the function which maps a finite sequence to its length is a grouping. Another example. If we have the set of directed simple graphs over a set X, then we will group this with a function which maps to the number of edges on the graph. Another common grouping for such graphs is a function which maps a graph to a pair where the first element is the number of vertices and the second element is the number of edges. For a given group, the worst case cost is the least upper bound of costs among the inputs in the group. For a given group, the best case cost is the greatest lower bound of costs among the inputs in the group. For a given group, the average case cost is the average cost among the inputs in the group, assuming a random distribution over the input set. Example, suppose we use insertion sort to sort finite sequences, and we are interested in the number of performed comparisons between the numbers. Suppose we group the input set by the length of the sequence. The worst case cost of insertion sort is a function from the natural numbers to non-negative real numbers, such that fn is n-1 times n divided by 2. This occurs when the sequence is in decreasing order. The best case cost is a function given by the maximum of n-1 as 0, and it occurs when a sequence is in increasing order. The average case cost of insertion sort is equivalent to n squared, when we assume that any inversion set for a sequence of length n is equally probable. Grouping is a tool, not a necessity. For example, suppose f is a function from integers to non-negative real numbers, such that fn is the maximum of minus n and 0. And suppose we group the integers by absolute value. Then the worst case cost function is a function from the natural numbers to non-negative real numbers, such that hn equals n. In this grouping, we lose information and do not gain much more intuition.